Thanks everyone for joining. Can everyone hear me well? I will take that as a yes. Okay. So the topic today is leveraging Airflow, Kubernetes, automatic speech recognition, and parallel processing to gain insights over customer calls. But before proceeding, just a quick round about myself. As Jesse mentioned, I have around 13 years background, mostly in technology in different areas. I have a background in software engineering, Master of Science degree in Information Studies and Data Science. In my career, I focused mostly in financial markets, but also in some different industries like retail, energy, IoT, and some different businesses. Many different technical roles: software engineer, data engineer, data scientist, machine learning engineer, but also project and product management. And since December, I'm part of ING Customer Dialogue Analytics team. Really happy to be here. And my main interests are systems architecture, cloud architecture, microservices, machine learning engineering best practices, and MLOps. Okay, going to our topic. Before diving deep into the technical details, some business context. So in customer dialogue analytics, one of the hottest topics for us is customer service digitalization, right? And as you might be aware, we have many different types of channels for customer service. And today we're going to focus in two of them. So interactive voice response and phone and video, mostly phone through human agent calls. So for digitalization as a strategy, we are talking about focusing on the digital channels, and digital channels in this case, not only IVR, but also chatbots, email, and chat. The idea here is to focus on these channels and reduce the amount of time that we need to spend with human assistance. By that, when we say that, we're basically saying that we want to increase deflection by reducing human assistance, unless it's totally required. And to achieve that, we need to decrease fallback. And just to contextualize a little bit further, fallback happens whenever it's not possible to get assistance through any of these automated channels. So when you're talking to an IVR and you hear a recording say, "Okay, sorry, I didn't understand what you said. Please wait while I route you to a human assistant." That's basically a case when you're having a fallback. It's really important to reduce that. But how to increase deflection or how to decrease fallback? These are two things that are closely connected, and we need to tackle both of them. Well, a little bit of a glance about customer calls at ING. ING is one of the biggest banks in Europe and in the world, so you would expect that we have a huge volume of customer calls. So taking the Netherlands as an example, we have around 400K monthly calls to interactive voice response. Out of this total, around 40% end up with a human agent. So as we can imagine, there's a huge resource optimization opportunity. If we're able to decrease these to 20% or even 30%, that's already a huge gain, not only financial, but also operational-wise. But when we talk about fallback and human intervention, we have different reasons for that to happen. It can either be because of complexity and security purposes, for example, when it's a case like credit card fraud. But it could also be that the customers are asking about intents that are still not expected, are still not covered by our flow. So in order to tackle that, it's important to do a qualitative analysis over the full conversations that happen between the customer and the agent at ING. We need to understand what kind of topics are being discussed, but how to do it at scale. Well, a good idea is to leverage automatic speech recognition. And in order to use that, well, when we started talking about this, we already had the transcript for IVR opening sentences, which means that we already had the text for things that customers were asking in the opening sentences in IVR, but we still didn't have the transcribing engine for full conversations. So this was basically not available at the time. So we said, okay, let's do some market analysis. Let's see what's out there. We have different options in this case. Obviously, cloud providers like Google and Azure and AWS, they provide this as an offering. And for languages like English, for example, they have really good offerings. But we also have some niche providers, some smaller companies, and some of them focus in languages like Dutch and other least popular languages. So we have these two avenues that we explored. And well, you always have a trade-off in terms of complexity, performance, and also privacy. If you want to run anything cloud-based, we need to think about privacy. On the other hand, if we're able to run any kind of solution for that on premise, in terms of privacy, it's a better solution. But it's always a trade-off between these three topics. So in order to get started with a minimal viable product, we did a bit of market analysis, some scanning in the market. We had a group of runner-ups, and we ended up evaluating the offerings from Google, as you can see here, depicted in this plot. But we also evaluated a smaller company which had a focused offering about related to the Dutch language. And for this MVP, Dutch language was our focus. So what we did was to evaluate multiple different types of metrics. We're going to focus today on this one, which is word error rate. And the idea was to confirm, okay, if we go to more niche players, can we get more performance? And in fact, for this exercise, the conclusion was yes. We were able to find a more tailored engine, and what we did was a partnership with this company, so that we could create a really tailored solution for transcribing text in Dutch language, not only for Netherlands but also for Belgium. Right. So this was the first step. This was the winner. But then it came the time to implement some kind of actual MVP for that, technically speaking, right? And the way that we did this, we are depicting here in kind of a high-level vision. So basically, it all starts here. The customer makes a call to the IVR, which runs on Twilio. We have an intent detection model for call routing purposes based on dialog flow from Google. This is used for routing the customer to the right answer, or sometimes to the right human agent. When the customer talks to the human agent, after that call has taken place, we also want to do two things. First, to run a more fine-grained intent classification model, also using dialog flow, but to detect the intent that is related to the IVR opening sentence. But not only that, what we did in this case was to download the full conversation from Twilio and run the transcription engine, which is based on a Docker container. So this more about the steps at a glance. If you think about, okay, what are the outputs that we got from this process? Basically, we get a text output. For each and every conversation, we get a JSON file with each and every word, the confidence for prediction of each of the words, duration, time, and of course, which word is being spoken. But then also nice to zoom in a little bit about this step here, and we will do this in the coming slide. So here, from the perspective of this MVP, we are talking about some different components running in the same virtual machine. So First step, of course, we need to download the audio files in this virtual machine. After that, we have a Docker container, and we have different steps that are part of this pipeline. First of them, we need to perform diarization, and diarization is basically segregating the conversation into multiple channels. So you always have two people talking in a conversation. So in this step, we basically separate the audio from the agent from the audio of the caller. After that, we are able to run the transcription. So we run transcription for both channels, and we end up with a text file containing the full conversation, all the words that were spoken by the agent, but also by the client. So this MVP solution, as I said, is based on a virtual machine. As an output, we get a text file, and in terms of scheduling, it's a batch process. So the way that we scheduled this was through a simple cron job, which basically triggered a job based on a paper mill to run the steps from a Jupyter notebook. Plain and simple. But what are the challenges with this setup? Well, we have a couple of them. The time required to transcribe each conversation on average is around 6 minutes. So what we ended up doing was running the automatic speech recognition engine over a random sample. It's infeasible. It was infeasible to run over the full sample. And another challenge was that we are talking about sequential processing. Basically, the idea here was to process each of the files one by one, which is good for validating the idea, but not the best in terms of throughput. Here we're not able to talk about task and dependency chaining. So if we want to chain different actions taking place after our transcription pipeline is completed, it is a bit cumbersome in the setup. In terms of fault tolerance and retry mechanism, it also becomes difficult to manage that with a simple setup like that. And other things like, for example, alert and monitoring and credentials management and scale in terms of scalability as well. So after some analysis, we ended up with this list of challenges, and we thought, okay, what would be the target solution to overcome these challenges? Well, one of the first items is, okay, we want to have some degree of dependency chaining, because after we perform the transcriptions, we can run some processes to generate additional insights or storing them in a database, performing some ELT processes to make it suitable for some analytics workloads and some other kind of steps. In order to increase the throughput, we also wished to run multiple containers, not only one container, but multiple containers in parallel. But then, even if we run multiple containers in parallel, it's also important to have the appropriate monitoring and alerting and some retry mechanism as well. In case of anything fails, we want to automatic retry. We wanted the solution to be fault tolerant as well, and some secondary features, for example, as credentials management, to store the credentials encrypted, and to have some flexibility in terms of scaling, being able to not only vertically but also horizontally scale would be also great. And last but not least, we could do all of these, but if we don't store the data properly in a way that is easy enough to run queries on top of it and generate valuable insights, there will be no point. So we also wanted to have a data warehouse to store this data. Okay, so how do we achieve these? We talked about these requirements, but in terms of a solution, in terms of the design, what we were talking about was basically this. So here we have multiple audio files that we want to process, And we want to spin up multiple containers as we wish. And as these containers are spin up, each of these should process multiple audio files in parallel. This way we can guarantee that we can easily control the throughput by spinning up more containers, so we are performing horizontal scaling. And then each of these containers, once the transcription process is finished, we store the resulting output in a Postgres data warehouse. Right. With this design in mind, we thought, okay, what would be the best tool for the job? Well, it didn't take long for us to realize that we could use two different tools, which could be helpful in this case. And these tools are Apache Airflow and Kubernetes. And the nice thing here is that Apache Airflow as a tool has a really nice integration with Kubernetes, some really nice features, which we're going to explore. We're basically talking, when we merge these two words together, we're talking about a really powerful combination. So some features of this setup are each of the Airflow components run in one or more Kubernetes pods. I won't spend too much time talking about what is Airflow because I think everyone or most people are aware. But this is really a nice thing. Airflow has different components, task scheduler, a web interface, and the workers. So it becomes really flexible to run this setup in a Kubernetes cluster because each of them is running a separate pod. And not only that, each of the tasks spins up in its own Kubernetes pod. So that opens up some interesting possibilities as well. We can perform a really dynamic resource allocation if you have multiple different tasks. When you write the DAG, you can define what are the CPU and memory requirements for each of the tasks. If you have one task that is more resource intensive, you can scale up the resources for that task. If you have some other simple ones, you don't need to consume all the cluster resources equally. You can tailor that in a way. And an interesting feature as well is that you can specify target nodes through pod affinity. So basically, you can define which nodes in the cluster are going to be hosting each of the tasks. Let's say, for example, that you want to specify a node which has access to a GPU because you want to train a deep learning model. You can easily do that by using pod affinity when writing your DAG task. And of course, we're talking about Kubernetes pods, which means that the tasks are container-based, and that means that we have easier dependency management. Each of the tasks has an isolated environment. In terms of the architecture, visually, what it means is that, as I mentioned previously, so here we have a Kubernetes cluster. Each of these icons represents a pod. You can have different pods running different Airflow components. In this case, the web server, which is the graphical interface, the scheduler, which basically coordinates the different tasks, a metadata DB, which stores the task schedule and definitions and requirements. And of course, you have the workers, which can be as many pods as you wish. Okay, so we came to the demonstration, which is the most exciting part. Unfortunately, we're not able to do a live demonstration because we would need to have access to the internal network. But what I try to bring here is basically the capabilities that we are talking about when it comes to implementing parallel processing and how we implemented and how we were able to achieve it. So in this picture, we can see the first version of this pipeline. So we start here with the first task. There is a task to download the audio files. perform the decryption. And the focus here, the most critical task in this case is this one, to transcribe these recordings. In the beginning, we were performing this, as I mentioned, sequentially, right? So we were thinking, okay, how can we parallelize this in the most flexible manner so that we don't need to change the tag or perform any kind of code change to increase or reduce the degree of parallelization. So the way we implemented this, so we have different connections that are used for this pipeline. Each of the connections has a purpose. So we have one connection for downloading the audio files, but the most important one in this case is the one that we have related to the container, which is used for the transcription. And what we did here was basically adding an additional parameter for specifying the degree of parallelism. And here, for this example, I've set up 10. The default is 1. If you don't have any value here, it's going to be sequentially. But here we can set up as many degrees of parallelism as we want. And what happens after we change this? Well, after we save these changes, this variable is referenced in the tag definition. So once this is updated, once Airflow reads the new definitions for this parameter, we implemented a dynamic tag so that whenever there is a change in that parameter, we're going to have a different number of tasks running in parallel for the transcription, which means here that each of these tasks will simply process one of the files, one of the audio files, which is still pending to be transcribed. And as long as there are pending files in our target data source, these tasks will keep running. Once all the processing is finished, then we will reach this state here. And after this, it's mostly downstream tasks. So we have one step for uploading the task metadata, and finally uploading the transcription to the database. And as I mentioned, it's we model this as an ELT process. So here we basically upload the raw data to our data warehouse, and we have a final step to perform some merging and to transform the data so that it is ready to be queried. All right, so which kind of results did we get? Right from the beginning, we are able to increase this capacity tenfold. It is really straightforward to increase the degree of parallelism here. It depends only on the parameter change and of course on resource availability. So if we push the hardware resources that are available in the cluster, we can push this even further. We can increase this to 20 or 100. We'll say that the sky is pretty much the limit here. In terms of resiliency, we have so far 99% success rate for the pipeline. And this degree of scalability also allows us to expand to other regions. So we have currently projects to expand this pipeline to Belgium and to Spain, and many other regions can follow as well. It becomes really straightforward to add more regions to the scope due to the flexibility. And last but not least, since we are storing this data in a data warehouse with some nice tooling, these unlock some interesting insights and metrics. We are able to calculate what is the silence rate on average for each group of agents. This is a nice measure to compare what is the percentage of silence during the call, because that can directly affect the customer happiness with the service. We can also measure, do some quality analysis and check if agents are adhering to call scripts depending on the different teams. And by analyzing this data, we can also understand if there are new customer needs. If we see that it's common that customers mention new products or some new issues that they're facing in the conversations, we can take some measures in order to improve that. And this more of an initial insight perspective. Of course, there are many more use cases that could be explored. We could perform sentiment analysis over the calls, entity recognition, and any other interesting use cases. Well, with that, we wrap up. I want to thank you. If anyone wants to connect on LinkedIn, feel free. I also write frequently in this blog, MLOps How To. If anyone is interested in machine learning engineering, MLOps, feel free to browse. And I think now we can open for some questions.
Thank you, Rafael. It was a very nice presentation, and we have some questions from the audience. Robert Moline asks, first of all, yes, great insights. Are you able to detect sentiment and intent from the call during the call, or were they always processed afterwards?
Good question. Right now, we are talking about more of a batch processing paradigm, which means that once every day we go there and we perform these, we get these transcriptions. So right now, with this current setup, it's not possible, but it is in our pipeline to get the transcriptions in real time, so that you could generate some insights on the sentiment or some additional insights that could help the agent in real time.
Okay. Then we have another question from Dennis from Felsen. Sorry if I mispronounced your name. Is the source code available? Is it open sourced?
No, for this specific engine, it is developed by a third-party company. But with that said, there are currently some other options in the open source world. Facebook just open sourced wave to vec model. That's really interesting. Has some really interesting figures. And I'm pretty sure there are many other options, but for the case of this one, no, it's not open source.
Okay. And John asks, have these insights and metrics resulted in actual changes in these calls or the performance of these conversations?
Right now, we are in a stage more about exploring these insights, and of course, there will be some effort as well in trying to prioritize which of the insights to tackle first, right? And for that, we depend also on a bit of insight from the business as well. So right now, we are currently working together with our end users to define what to tackle first.
Okay. Then we have another question. How complex is your ETL setup? Meaning, how many jobs run and at what frequency?
For this one, currently it's not that complex. For this first version, we are basically talking about one batch process where we do two things. As I showed in the slide, as an output, we get currently the words, so a high level of granularity. What we do is some transformation to aggregate that on the sentence level. But not only that, we also group that depending on the different agent queues. So if I could summarize it, it's basically the ELT that we have right now is basically for aggregating under these two dimensions. But of course, as we improve these and start to have more sophisticated use cases, we'll probably need to have more transformation batch processes.
Okay. Yeah, if someone else or anyone else have any more questions, please reach out to us and we will move on to our next presentation. Thank you, Rafael.
Thanks. It's a pleasure. Yeah. Thank you.